Now we will discuss about uh, how to find the arc length of a curve if it is given in polar equation. So, let us try to see arc length. So, now for our purpose, this is given r equal to f of theta, which is a function, and let us say a is lesser equal to theta is lesser equal to b. So, we want to find the arc length of this curve. As we recall, so there what we are trying to get in the parametric form, we are getting the dx by dt and dy by dt. So then we are taking the square of dx by dt, and then the square root, we are finding the length. So the similar method we are going to apply here. So here x is equal to r cos theta and y is equal to r sin theta. Therefore, dx by dt d theta is equal to dr by d theta cos theta, then minus of r sin theta, and dy by d theta, this is equal to dr by d theta sin theta plus r cos theta. So then we need to find dx by d theta square plus dy by d theta square. This is equal to dr by d theta cos theta minus r sin theta square plus dr by d theta sin theta plus r cos theta square. This is dr by d theta square, and then we get a cos square theta here, sin square theta here, if it adds up to 1, and then minus 2r dr by d theta cos theta into sin theta. Here we are going to get plus 2r dr by d theta sin theta cos theta, that gets cancelled, and here we get r square sin square theta. Here we are going to get r square cos square theta plus r square cos square theta. So that is going to be 1. So now the arc length we get is L, which is equal to a to b square root of r square plus dr by d theta square, then this is d theta. This is what is the formula for the arc length in this format. So the method, as we see, we have done it for the already we have done it for the parametric curves, and this is. Let's do some example. Find the length of the cardioid r equal to 1 plus sin theta. So now here the interval what we are looking, theta is varying from 0 to 2 pi. Now r equal to 1 plus sin theta, therefore let us calculate dr by d theta. So this is going to be nothing but cos theta. So length will be equal to 0 to 2 pi 1 plus r square is sin theta square plus cos square theta, then the square root and d theta. So, which will be equal to 0 to 2 pi square root of 1 plus sine square theta plus 2 sine theta plus cos square theta d theta, which is equal to 0 to 2 pi square root of 2 plus 2 sine theta d theta. So, which is equal to, you can take it out, the square root of 2, then 0 to 2 pi square root of 1 plus sine theta d theta. And you can compute this 1 plus sine theta square root of sine theta d theta by various method what we know. So, and once you compute that, you get the length of the curve of the cardioid. Okay, so this what we have seen till now is that it is as an application of Riemann integration. We can get the area of the region bounded between the two curves, whether it is given in the form of Cartesian coordinate, the y equal to f x, or if it is given in the form of polar coordinates r equal to f theta. So, r equal to f theta, what we have, y equal to f x, what we have done is that the Riemann integration with the Riemann prescription of taking the Riemann sum, we used to get the rectangles, then sum up all those areas of the rectangle after partitioning the domain, and then we approximate that to get the Riemann integration. So, here in the area, what we for the polar coordinates, what we do is that we we get the partition of the theta varying from some alpha to beta, then the sector what we are getting, we approximate it by circle. So, this is going to be, each sector is going to be a portion of certain circle. We find the area and take the Riemann sum. Prescription is the same. Now, here it is a word of caution. So, this we know that this is going to be valid when we are talking about this to be Riemann integrable and other thing for this L. So, here we can say that f prime is continuous. So, that is going to guarantee with this additional condition that this integral makes sense. So, we are going to get the arc length of a curve. So, not necessarily that every curve we are going to get the arc length like this. So, whenever we can find the arc length, what we say is that this is a rectifiable curve, and in our case we have, for our own benefit, we have assumed that f prime is continuous. We can relax this condition a bit, but we are not going to discuss that issue here. Now, let us move into another application of Riemann integration. So, by using Riemann integration, we can find the volume of certain solids. So, we have found the area of the region. Now, we are going to calculate the volume of certain solid by using our knowledge of Riemann integration. Okay, so let us see. So, now we have let us say x equal to a. So, we have x equal to a here and x equal to b here, and we have a solid something like this. So, this is what is a solid which is we are interested in finding the volume. Now, think of it, here is the function which is defined from it goes from x equal to a to x equal to b. So, we take a partition, consider p which is equal to a which is equal to x naught less than x 1 which is equal to b. Okay. Now, here are the points. So, this is let us say x 1, this is some x 2 like this, and this is equal to x n. Now, look at the plane perpendicular to the x axis at this point. So, if you make a slice of this plane, you think of a knife you are putting it perpendicularly. So, now you are going to get a surface. So, here if you take the plane, just slice it, then whatever what you are going to get on the plane, you are going to get a something like this is the plane, and here you are going to get this plane is with a little thickness, what you are going to get is. So, now you find this area of this surface. Now, there is certain thickness. So, slice slice slice. So, now if you find the area of this surface, which is a two dimensional thing, we can find the area of that surface. Essentially, this is going to be the area bounded by these two curves with this is the region, we know how to find the area. So, consider planes perpendicular to x axis at x equal to x I from each partition point. So, now you will get slices, n slices. So, the area, consider the slices of the solid that is bounded by x equal to x I minus of 1 and x equal to x I. So, which means on this it will look like something like this. So, which is a small a thick slice depending on how small you are taking your partition. So, now what do you get? The volume of this slice is approximated equal to the area of the surface into x I minus x I minus of 1, that is the thickness. This is what is. So, where A x I is the cross sectional area that is made by the plane. So, when you are cutting, so this is the cross sectional area and this is the thickness. So, the volume what you are going to get this area into the thickness of this, that is this. So, this is what is the going to be the volume. So, now what the Riemann prescription said? The natural, it is natural to consider the Riemann sum. So, consider summation over I from 1 to n, this A x I. So, this is delta of x I. So, now what is the method? So, you make this partition smaller and smaller, then you take calculate this volume which is given by this. So, that is what when it this is going to be a Riemann sum. So, now if we take the limit, then what we are going to get? So, volume, because you see the point is that here this is you are getting the volume approximately to the sum of this n surface area into the thickness. So, take finer and finer n. So, that is what we have done for in our earlier experience. So, the volume, this is definitely going to be A is going, x is varying from A to B. So, this is A x dx, that is what is the simply the volume of the solid, sum of the solid what we can get by slicing. So, let us do some example. Find the volume of the sphere of radius r. So, now you have a sphere of radius r. So, now if we are slicing it, the plane, if we pass through the plane, cut the plane. So, what you are going to get? What is the surface you are going to get? You are going to get a surface of, this will look like a circle. Now, in this circle, here you are going to also, if you cut at this point with a partition, if you are taking, then this is the circle. Now, this circle, suppose this is the origin, if I am taking the volume of the sphere. So, let us calculate the volume. With origin as the center. Well, so now this is your x, this is going to be r. You do not need to even consider the origin, but just so now this is going to be the y. Now, this if we are cross sectioning, then with the centered at x, when you are going to get what is the cross section you are getting? You are getting the cross section which is a kind of a circle, a disk, what you are going to get. And now, what is the radius? Radius is nothing but y. So, therefore, the area is going to be pi y square. So, now y here by the Pythagoras theorem, y equal to square root of r square minus of x square, because this is what is the y. So, the volume, so the area of cross section so the area of cross section is nothing but equal to pi y square. So, therefore, this is equal to pi of r square minus of x square. So, the volume is equal to, now the x is going to vary from where to where? This is going to vary from here on this side minus of r and to up to r. So, this is going to be minus of r to r, and a x is equal to pi r square minus of x square, then this is dx. So, which is equal to pi times this is r square of x minus of r to r, and then minus of x cube by 3 minus of r to r. If we calculate this, this is going to be 4 by 3 pi r cube. That is what we know, that is the volume of the sphere with radius r. Okay, so now this is the circle, this is we can get it by the slicing. Also, you know, when the surface which you, if we are revolving around the axis, then we have a given a curve. Let us say we had given some curve like this, any curve. If we revolve it around the x axis, so what we are going to get? Something like this. So, now when we try to, so now our x varies from this a to b. So, now if we, when you are revolving, when you are cutting it down, then with a plane, if we cut down with a plane, then what you are going to get? This is you are revolving. So, inside you are going to get a circle, something like this. This is the cross section. So, we can find the volume of this sort of surfaces. So, let us take for example, do it a concrete example, or find the volume of the solid obtained by rotating about x axis the region under the curve y equal to square root of x from 0 to 1. So, what is it? So, we have a curve y equal to square root of x from 0 to 1. Now, we are going to rotate it on the x axis. So, what kind of shape what we are going to get? If we rotate, then this is going to be. So, now if we take the cross section, this is what you are going to get, right. You are rotating, so you are going to get the circle. So, therefore, what is the area of each of this cross section? Area is going to be the pi r square. Now, what is this r? R is the center is here. Now, this is what it is going to be the radius of the circle you are getting in the cross section. Now, this radius is nothing but square root of x, because this is y, this is the square root of x. So, a cross section area is equal to pi into square root of x square, which is equal to pi x. So, let us go to the, so the volume is 0 to 1, that is what you want to get, and then this is pi x dx which is equal to pi times x square by 2, which is equal to 1 by 2 pi by 2. So, similarly, now we have seen it in the case of the finding area. What we see is that sometimes it is much more easier for us to consider x equal to f y. So, the partition what we are taking in that case, the y axis as the interval domain of the function. In this case also we can do the same example. Consider this is, let us say, y equal to x cube, and then let us get it up to 8, which is going from 0 to 8, y is going from 0 to 8, and we rotate this along the y axis, rotate along y axis. So, what do you get? You get a picture like this is a basket, and here if I, instead of I take the plane which is perpendicular to x axis, here if I take the plane which is perpendicular to y axis, then what I am going to get, the cross section is something like this. Right. So, now the cross sectional area is nothing but the pi of r square, this is going to be the r. So, therefore, the cross section area so now what is this? This is the radius what we are taking. So, now the x equal to, this is x. So, now this x equal to y 1 upon 3. So, therefore, cross sectional area is equal to pi y 2 upon 3. So, volume is from 0 and we are going up to 8. So, 0 to 8 pi y 2 upon 3 dy. Now, if we compute that, what you are going to get, that this is basically 96 by pi. Okay. So, now suppose we have a region, another example, we will suppose I have got a region something like that which is bounded by. So, now this I am rotating along the x axis. So, what I am going to get? I am going to get that this is the picture something like now. In this case, if I take the cross section, so what I am going to get? I am going to get this and this. Suppose this is, if I take this as to be my curve y equal to x square and this is y equal to x is the line. So, therefore, here this is x and the smaller one is x square. If I want to take it up to 0 to 1, x is 0 to 1. Therefore, the cross sectional area is equal to pi of x square minus pi of x to the power 4. So, the volume is equal to 0 to 1 pi of x square minus x to the power 4 dx, which if you compute, you easily you will get that this is equal to pi times 1 by 3 minus 1 by 5. So, 2 pi it is 15. Because you see, so if you take the cross section here, then you are going to get a bigger circle and this is going to give you a smaller circle. So, therefore, the area is going to be the, this is what you would like to get, because you are going to get the hollowness inside this. So, this cross section is nothing but this area minus of this area, because if you rotate like this, then what you are going to get a solid which is something like this, and inside it is hollow. So, this is also this sort of surfaces we can find the volume by using our Riemann integration. This is also an application of the Riemann integration. So, in the next lecture we will also see, can we increase the class of functions which beyond this condition of the boundedness continuity for the Riemann integration. That we will discuss in the next lecture. Thank you.